So in this video I'll solve problem 339 in Hibbler. So this is a pretty straightforward, well, it's a little bit of a twist on an axial deformation problem. Really, the axial deformation of this is relatively easy, okay? So what the problem is asking for here is, here's a rigid beam supported by two rods, A and B, at A and B. They have different lengths. Here's a fixed force, but it's put at an undetermined distance. Now, depending upon where the force is located, you're going to get different reaction forces at A and B. What they want you to do is find the the position of the reaction force, the location of the reaction force, X, such that this beam remains horizontal. In other words, such that the deflection at A equals the deflection at B. All right? So the amount that this moves down is equal to the amount this moves down. Now, if these were the same lengths, that would correspond to the same the same strain, and therefore the same stress, and then the same reaction force at A and B. But since they're different lengths, this one will have to have a little greater strain because it's shorter, and therefore a greater stress, and so a greater reaction force in it. And they're the same material, the same diameter. Okay? So let's solve that. So there's really two parts to it. One is to determine the reaction forces in terms of X, and then also to look at the elongations. And you can do those steps separately, and then find X such that the elongations are the same. Okay? So again, if we draw the picture, here's, oh, that's not so good, but okay, bear with me. That's supposedly the rigid beam. We have a reaction force at A and a reaction force at B, reaction B. And then here's the 80 kilonewton force downward, and it's at a distance X in from point A. All right? And the constraint has to be that the elongation in A has to equal the elongation in B. And in this case, actually, it's going to be a compression, right? So this is delta B, and this is delta A. And if they're equal, then the beam remains horizontal, even though I've drawn it terribly unhorizontal. Okay. All right, so as I said before, there's kind of two steps. One is to get the reaction forces in terms of X, and then the second one is to get the elongations in terms of the reaction forces, which will then give me a relationship in terms of X. So once I find the reaction forces in terms of X, I can use that in this relationship to get this constraint equation involving X and then solve for X. So those are the two steps, okay? So first, I'll write it out. Find RA and RB in terms of the unknown X, and then we'll find delta A and delta B in terms of RA and RB, okay? And then the last step, well, we can use what we find from step one, put it into the equation we get in step two, and then we'll be able to solve for X, okay? So we'll be able to solve this equation here for X, but it'll be in terms of X, okay? All right. All right, so, well, let's do the first part. Let's find the reaction forces in terms of X. So let's do a sum of moments around point A. That equals 0. So that gives me that minus 80 kilonewtons times X That's the moment of this one around point A, plus the reaction B times its moment arm, which the book gives you as 3 meters, has to equal 0. Or in other words, RB equals 80 kilonewtons over 3 meters times x, and then x will be in meters, and that gives me RB in kilonewtons. And so when you do that out, this becomes 26.7 kilonewton meters times x. That's RB. Okay? Now we can do sum of forces in the y direction equal to 0, and that gives me RA plus RB equals 80 kilonewtons. And I can use this equation into here to explicitly solve for RA. That gives me that RA is equal to 80 kilonewtons minus RB, which we know from up here is 26.7 kilonewtons per meter times x. All right? So here's RA and here's RB. Okay, they're both in terms of x, so x is unknown. Okay? All right, let's move on to the next step where we find the elongations. Okay? Well, this actually isn't in this chapter, it's in the next chapter. But since I already covered the material, the derivation is actually built into here. But to do that, you would know that the elongation, is equal to the normal force in the element times the undeformed length of the element over the cross-sectional area times Young's modulus. Now, in this case, the internal reaction force and L for elements A and B are going to be different, but A and E are the same. So A is equal to, well, let's just do AE. AE is equal to pi on 4. The diameter of each element is 30 millimeters, so that's 0.03 meters squared. Well, I should do this one. Squared, right? That's A. And then E, for aluminum, it says it's aluminum, in terms of PSI, is, 73 gigapascals. Okay? So that's Young's modulus for aluminum. And then if we do that calculation, that gives me so that gives me 516.4, and that's going to give me units of, well, this is 10 to the 9th, 10 to the 6th, so that's mega newtons, 10 to the 6th units. Yeah, 10 to the 6th. No, not units, newtons, right? And that's a consistent units because this is force per area, this is area, so that works out to be newtons, okay? That's AE. Okay, that's going to be the same for both. This is the same for A and B. All right, so what that's basically saying, actually I didn't even need to calculate that because we want this constraint, well, the elongation in A is going to be the force in A times the original length of A over this AE, that has to equal the elongation in B, which is the force in B, over the length in B divided by AE. So I can simply write this, the AEs will basically cancel out the equality, and that'll give me that the force in A times the length in A has to equal the force in B times the length in B. Okay? So that's the way they scale. So this is the equation that ensures that the beam remains horizontal. Okay? That's that equation. That's the equation that ensures that the two beams remain horizontal. Now the reaction A, this is going to actually be negative RA, and this one is negative RB. Just to be careful with the signs. Now in this case, it doesn't matter, they're the same signs. If you put them as positive, you actually will get the same answer. Okay? But let's put them as negative. The negatives cancel out anyway. So this gives me actually a better relationship. We'll say RA times the length in A equals RB times the original length of B. All right, so let's use that actually. This is going to be the result from step 2. All right? So what we can do now is we can use these relationships in here, and then we'll have everything in terms of x. Okay? Okay, let me just pause it here. All right, sorry for that pause. Where were we? Okay. So we'll use this relationship, and we'll substitute in the relationships we got in step A for RA and RB, but in terms of x. We know LA and LB. I mean, I should have put these in here already. Where'd my pen go? This is LA is 200. This is 0.22 meters, and this is 0.21 meters. Okay? So basically, another way you can look at it if you want. Well, we'll leave it that way. So this is telling me that rewriting this, substituting, let's call this equation 1A and 1B. We'll call this equation 2. So putting 1A and 1B into equation 2, we'll get the following. Okay? We get 0.22 meters times RA, which from before is 80 kilonewtons minus 26.7 kilonewton meters times x. So this is RA. That has to equal 0.21 meters times RB, and from before we got RB is 26.7 kilonewton meters times x. All right? So I'll call this equation 3. All right? So it's just an algebraic equation we now have to solve. We solve equation 3 for x. Okay? I guess like the cooking shows, I probably could have done this like offline, right? Solve this and then give you the result, because it really is just algebra at this point. But let's do it. So we want to combine the like terms of x. Let's divide by 0.22. So we'll put this over 0.22 meters. The meters cancel out, so we don't have to worry about those units. That gives me 80 kilonewtons minus 26.7 kilonewton meters times x equals this. Let's do that math out now. Get 0.21, enter, 0.22 divide times 26.7 This gives me 25.5 kilonewton meters X. And now we can combine these two. Let's subtract this. I'll get 80 kilonewtons equals, doesn't have decimal place there. And we subtract from the right-hand side 26.7. They're the same units, so I don't have to worry too much about that. That gives me a minus 1.21 kilonewton meters X. And now we can divide by that, or 80 kilonewtons divided by a minus 1.21 kilonewton meters X. Oops. Equals X. And that's going to give me a negative result, which I'm going to have to then explain to you why it's negative, or why I screwed up and it became negative. All right. Let's just do division, get the numbers first. So that gives me wow, what did I do wrong here? Minus 66.1 meters. All right, so that's not practical. Something happened here. Let me pause. Not good. All right, that's pretty good, actually. I like this, being able to pause the videos, because now I figured out where I screwed up. And you probably all figured it out already. It's usually students figure out where I screw up before I do. So obviously what I did here was I subtracted this, but I needed to add this to both sides, right? This was a minus, so I add that. I took a subtraction, and that's what screwed me all up. Flip the sign. So when I add the two, it gives me 26.7, enter, and 25.5. Add the two. This should in fact be 52.2 kilonewton meters times X. Now when I divide here by 52.2, again that's still kilonewton meters, that'll give me X equal to 1.53 meters. So a much more reasonable number. That puts me, obviously a negative 66 would be off the beam, but X is positive this direction. So that means that this distance here should be 1.53, a little over halfway, because the whole length is 3 meters. Okay, and this is the 80 kilonewtons. Okay? All right. I think the other thing it wants me to do here, though, there's a second part to the problem. It wants me to figure out the diameter of the cylinder after the load is applied. And on my photocopy, I don't see which cylinder. Because obviously, the stresses are different and the strains are different. So the diametric change is going to be different because of the different strain. So that one's pretty easy. I guess since we're in this chapter, I should finish that one off. So let me do that. That's the second part, is to find the change in the diameter. And I'm not sure which one it's asking for, because I clipped that off in my photocopy. But let's do A. B goes the same, obviously. All right? So to find the change in diameter of A, and it tells you for aluminum, Poisson's ratio is 0.35. So the change in diameter, well, the diametric strain is equal to minus the Poisson's ratio times the longitudinal strain. So we will have to go and find this in element A. Then we'll be able to find this. And then using that, we can get that the change in the diameter is equal to diametric strain times the original diameter. Okay? So we take this, I'm going to solve for this, put it into here, and that will give us the answer for the change in diameter. And I'll just do A. B goes the same way. All right. So I need to go back and get the strain. So we need to find the strain in A. Okay? Well, I know the reaction force. Well, actually, it's even easier. I know that's the change in length over the original length. I already figured out, well, I can figure out the change in length from the equation I had. So, the change in length. I should stop here. There's actually two ways you can imagine doing this. You can get the strain by figuring out the reaction forces. Then knowing the reaction forces, you can get the stresses, and then using Young's modulus, you get the strain. Actually, probably that's what the book intends you to do with this problem. Since I used the elongation formula, I got delta L in the first part, and I can use delta L over L, the strain definition, to give me the strain in A. All right. So there's probably two ways to do it. Okay, so let's figure out the elongation in A. I can get that right here. You know what, actually, let me pause, let me start, and I'll make a new video from this point on, okay? So let me